Right, June 21, paper 52. So the first question, we are looking at the enthalpy change of the reaction between anhydrous magnesium sulfate. So there are two types of magnesium sulfate here. The first one is the anhydrous, which means there's no water in that formula. And the magnesium sulfate with 7H2O is the hydrated. So just because there are 7H2O in that formula, it doesn't mean that it is an aqueous. Okay, it's a solid. The water is locked inside the solid as crystals. Okay, crystal like solid H2O. But they're just really tiny water molecules inside the formula. So when you touch the solid, it shouldn't feel wet. It's like a normal wet precipitate. Okay. Okay. The enthalpy change cannot be measured directly. Predict whether the enthalpy change for this reaction is positive or negative. So with enthalpy, it's not easy to see whether it's going to be exothermic or endothermic. You either know it, you know the reaction, or you looked at the difference in energy. So there's not much you can tell in terms of energy, but bond breaking and bond forming is actually an exchange. There's an exchange of heat energy. Bond forming, you will take in energy. Bond forming, you will give out energy. Bond breaking, you will take in energy. Okay. So what's happening here is that the 7 molecules of water will now be locked around the magnesium sulfate. Okay, so that looks like a bond formation to me, right? It's not straightforward, but I can tell you the explanation to why this reaction is exothermic. It's because it forms a bond between the magnesium sulfate and the 7 water molecules. Okay, so our prediction is that the reaction is negative due to bond formation between magnesium sulfate and H2O. Okay. Then there are 2 experiments. The first experiment is to dissolve the anhydrous magnesium sulfate. The moles are given. The volume of distilled water is also given. Experiment 2, same thing. We want to dissolve the hydrated version. Same number of moles and also same volume of distilled water. Okay. Results for experiment 1 are shown in the graph of temperature against time on page 3. Draw and extrapolate the cooling curve. So whenever you get a curve for enthalpy change, you usually draw 2 curves. One is the curve or a straight line before the addition of the reactant. If you haven't already noticed, the reason why the temperatures are constant here is because the reaction hasn't started. Okay, magnesium sulfate hasn't been added to the water. And then it looks like after 180 seconds, we start to see an increase in temperature, and then the temperature started to decrease again. So cooling curve is a line of best fit, or cooling line is a line of best fit from the highest temperature, and then when it starts to decrease. That's how a cooling, what's the word that they use? Yeah, cooling curve. Well, it doesn't necessarily have to be a curve, okay? So if you look at the points, the cooling points are between these two circles. And strictly speaking, I should draw a line like that. But extrapolation means you extend. So I extend the line and imagine that I have a line, a vertical line at t equals to 180 seconds. Okay, so that's my gray line. The reason for that is because I want to find the intersection between my cooling curve and T equals to 180. Why do we extrapolate? Now, this is a heat enthalpy reaction. And with the heat enthalpy reaction, there will be heat loss. No matter how good or how insulated your experimental apparatus are, there will be heat loss. So, based on our experiment, the highest temperature or the highest point is here at, I don't know, 26.4, yeah? Experimentally, the highest temperature is 26.4, but because of this extrapolation, my highest temperature is at the intersection. Okay, so there's a difference, right? There's a difference in actual highest temperature and extrapolated highest temperature. This is to allow or to compensate for any possible heat loss. So extrapolation is saying, no, actually, if we didn't have heat loss, our highest temperature would have been 27.5. Okay? So when you take the temperature change, delta T, you will take the highest point where at the intersection is, and the lowest temperature is where your line intersects the same T equals to 180 seconds. Okay, so how do you know this? You don't know this, but with practice, if you look at our practical papers where we do enthalpy change, you will see graphs that look like this. So this is your AS stuff. Okay, so delta T should be around 8.0 or 8.05. Did you guys manage to get that temperature change? Okay, maybe slightly different because, well, it all depends on how we draw our lines, but you should get your delta T to be around 8.0 or 8.05. Okay, I think I need a question paper, otherwise I'll have to refer. The anhydrous magnesium sulfate was not added when the timing started. So this is where the time was started at 0. There's no changes, so that must mean you haven't added magnesium sulfate yet. We wait for a while so that the temperature of the water in our styrofoam cup or in our beaker is the same as the room temperature. Okay, so that's the reason why we take temperature, but not much changes is happening. So you can see initially my temperature was a little bit warmer. As it equilibrates or equalizes with the room temperature, then we get a constant temperature that maintains at about, I don't know, what's that, 19.5? Okay, so the reason for that is to um, allow the temperature of the water to equalize. That just means to be the same. To be the same as room temperature. Okay. Next question. Outline the next steps that should be taken in order to obtain the results in experiment 1. So they want you to list down the steps that needs to be taken. so that you can get the results until you are able to plot the graph of temperature against time. Okay, so let's start. The weighing of the solid is done. That's out of the way. Okay, you want to add the water, right? So we start from there. First, we need to measure out, okay? Measure out how much water are we using for this experiment one? 50, okay. Measure out 50 centimeter cube. Does it mention what type of water? Tap water, distilled water? Distilled, yes. We must actually use distilled water because it doesn't contain any other ions, okay? So measure out 50 centimeter cube distilled water and then transfer to, what do we use usually for heat enthalpy or heat energy reaction? Do you use a glass beaker, a crucible? Do you remember? Kalau you use thermometer, what type of cup do you use? Styrofoam. And transfer into a styrofoam. We don't use styrofoam cup for fun. Styrofoam is supposed to minimize heat loss. Okay? Okay. All right. So before we add the solid, before we add the magnesium sulfate, if you look at the graph, what we did was we take the temperature of just the water. Yeah. What is um, what is the interval at which we measure the temperature? Every how many seconds? Every 30 seconds. Okay, so every 30 seconds, we record temperature. So that's before the addition of the solid. So record or measure the temperature of distilled water every 30 seconds before adding magnesium sulfate. Okay? And then at T equals to 180 seconds, what happens? What happens at T equals to 180 seconds? So you look at the graph, what happens after T equals to 180 seconds? The temperature goes up, right? So that means the reaction must have started, okay? So at T equals to 180 seconds, magnesium sulfate is added. Okay, then you continue to measure the temperature, but how do you make sure that the heat is being distributed throughout the solution? You stir, okay? So stir the contents and measure the temperature at the same interval, okay? Every 30 seconds. Or you can say at 30-second intervals, the same thing. Every 30 seconds until T is equal to what? When did you stop? T equals to 480 seconds. So T here is the time, okay? Don't get confused. Okay, next question is experiment 2. The student realized that when dissolving the hydrated magnesium sulfate, the amount of water present alters the total volume of water. So that means, if I draw a diagram, okay, when you add, say, the solid magnesium sulfate, okay, they will also give out Mg2 plus. So this is what happens actually, yeah, SO42 minus plus 7H2O. So this solid, after it dissolves, it will give out 7H2O. Oh no, that's the smallest Kasuda. Plus 7H2O. So there's some water being released from the hydrated solid and also the water in distilled water. The distilled water that you are adding. Okay, so the question is now, if, no, not the question. The problem is, if I add 50 centimeter cube of distilled water to the hydrated, there will also be 7 moles of H2O. So the total volume will not be 50. The total volume will be more than 50. Okay? So the question is now asking, so if I want the total volume of water to be 50, how much of distilled water should I add? Of course, I would need to add less than 50 centimeter cube, right? To make up for the 7 moles of H2O. So what I'm going to do first is I want to find the volume of this 7 moles of H2O. How much volume of water will this 7H2O contribute in the beaker? Okay, so first I'm going to write down the equation. Okay, so that's my aqueous. When I dissolve magnesium sulfate with 7H2O, the hydrated one, I will get magnesium ions, sulfate ions, plus 7H2O. Okay, I want to find volume. How much volume does 7 moles of water represent? Okay, so what do I know? I know the number of moles of magnesium sulfate. Okay, the number of moles is 0.0250. I know the mole ratio of my hydrated solid to water molecule is 1:7. Okay, so I find the number of moles of H2O from this hydrated solid. I can find the mass of H2O. I'm not interested in the mass, however. I want to know the volume, right? And to find volume, I need mass over density. Okay? The density is actually given in the question where it says, assume that 1 centimeter cube of distilled water has a mass of 1 grams. So the density here is 1. Okay? Density is the mass per volume. So 1 gram per centimeter cube, right? Once I found the mass of H2O, I can find the volume by using the formula mass over density. Okay, so this 3.15 centimeter cube is how much water will come from the hydrated solid. Okay, the question is asking, if I already have 3.15 centimeter cube of water, how much distilled water do I need to add on? How do I find that? I want the total to be 50. But 3.15 already comes from the solid. So how much distilled water should I add? How do I find? Minus 50 minus 3.15. Okay? So that's how you should do the calculation. Okay, so I will let you copy that down if you haven't done it. Did anyone try this calculation at home and manage to get the answer? Oh, okay, right. You can copy this down. Make sure when you copy it down, you understand what's happening. okay, what you are doing here. You need to leave early, right? Yeah, okay. Is it now or 2:30? Your parents here already? But okay. So the volume of distilled water that you need to add is not 50, but 46.85, okay? If you add 50, then the total volume will be over 50, and that's not what you want for this experiment. This experiment just wants you to add 50 centimeter cube. Okay, Renee, you can go now. And they also mentioned to give your answer to the nearest 0.05 centimeter cube. So that volume is to 2 decimal places. So I want you to think about that number and try to relate it to the next question. Okay, done? Okay, the next question asks you to choose a piece of apparatus to measure the volume of distilled water. Now, you want the distilled water to be accurate to 2 decimal places. What is an apparatus that will allow you to measure out this volume accurately? Burette. Okay, you can't use a measuring cylinder. Measuring cylinder will only read up to 0.1. Yes, 0.1. Okay, 0.1 centimeter cube. But for not even 0.1. 1 centimeter cube, sorry. 0.1 centimeter cube is the burette, and usually you can go up to half of that, half of the smallest value, okay? So the apparatus will be burette. The explanation is, well, burette can measure up to 0.05 centimeter cube. Can measure up to 0.05 centimeter cube accurately. Okay. Next question is the calculation. I think I know why you think it's difficult. The temperature change is added to the water is very small. So how do we make the temperature change bigger? Well, if you want the temperature change to be bigger, you add the number of moles. Okay, so more solid to be dissolved, the temperature will also increase even further. Okay, so just add the number of moles. Use a larger number of moles of the hydrated magnesium sulfate. Okay. Okay, next one, E part 1. So there are a few things that you need to look out for. For experiment 1, the energy is released. So you give out heat. It is an exo or endo? Exo, negative. Okay. 0.0250 moles of magnesium sulfate. You dissolve it in water, in distilled water, aqueous. So this is what happens. Enthalpy change of solution. Dissolve magnesium sulfate solid to form magnesium 2 plus aqueous and sulfate 2 minus aqueous. And the Not even the enthalpy change, but the energy is 2125 joules. You need to convert that to kilojoules per mole first. Okay, we'll do that in a bit. Energy absorbed by experiment 2. Absorbed means it's an endothermic process, positive, okay? By 0.0250 moles of the hydrated magnesium sulfate. The equation associated with that is dissolve the hydrated solid to form Mg2 plus aqueous, SO4 2 minus aqueous, plus 7 moles of H2O. Again, the energy is 477.5 joules. I want them to be in kilojoules per mole. So you can see that you have energy value for experiment 1. You have energy value for experiment 2. That means I've got the equation for experiment 1, equation for experiment 2. I can build what we call a Hess's cycle. As a matter of fact, you would need a Hess's cycle for this. Before building the Hess's cycle, let me just convert this number first, 2125 joules, okay? So the energy is 2125 joules. I want enthalpy change in kilojoules per mole. So what you can do first is to divide by 1000. That gives you the answer in kilojoules, okay? So this one, right? So enthalpy change kilojoules per mole is literally energy divided by the number of moles. Do you know the number of moles? Is it given? It's given in the question, right? 2.125 kilojoules divided by 0.0250 mole. You should get 85 kilojoules per mole, but don't forget the question mentioned experiment 1 releases energy, so it's negative sign. So this is the value. I call it that delta H sol 1, enthalpy change of solution for experiment 1. The second step, second part, is to convert delta H sol to, sorry, are you not done yet? Delta H sol to the same, following the same steps, okay? You take the energy, change the joules to kilojoules first, and then take the energy, divide by the mole, number of moles, okay? So that's delta H sol 2. I'll show you here, delta H sol 2. Again, divide by 1000 to give you the answer in kilojoules. So just ignore this divide by 1000. 477.5 divided by 1000 is 0.4775. So kilojoules per 0.0250 mole. And this is an endothermic reaction, so I just have the positive sign, positive 19.1. Are you all okay with the conversion of energy from joules to kilojoules per mole? Next, I will construct my Hess's cycle. How do I construct my Hess's cycle? So you look at equation 1 up here. Magnesium sulfate is dissolved to, magnesium sulfate solid is dissolved in water to form Mg2 plus SO4 2 minus. So same thing, MgSO4 solid dissolve to form Mg2 plus SO4 2 minus. That's equation 1, experiment 1. And I can label that as delta H sol 1, which is negative 85 kilojoules per mole. Experiment 2, MgSO4.7H2O solid will be dissolved into Mg2 plus, SO42 minus, and 7H2O. Same thing. MgSO4.7H2O solid is dissolved into Mg2 plus, SO42 minus, and 7 moles of H2O. So I can label this delta H Sol 2 plus 19.1. Now that's a complete Hesse cycle. I don't have to worry about the H2O because, well, if I dissolve H2O in H2O, there's no enthalpy change for that, okay? There's no reaction really, you're just mixing the H2O. Now my question is, in terms of 1 and 2, how do I find the delta H for this top equation? In terms of 1 and 2. How do I find delta H? 1 minus 2, okay? So I want to find delta H, which is, that's my resultant arrow. So going from 1 and up there, and that's the total opposite of reaction 2, okay? So the answer should be 1 minus 2. Did you get negative 104.1? Okay. The student noticed that some magnesium sulfate was left undissolved. So that means you have less number of moles reacted. So if you have smaller number of moles, the delta T will also be smaller. Same logic as just now. You want bigger delta T, you use bigger moles. So for this one, use, say and explain the effect. So it will now be small delta T. So if you remember, delta H is equals to MC delta T. Experiment 1 was exothermic, so it's negative MC delta T. If your delta T is small, what happens to your delta H? Negative small, okay? So then the effect would be less exothermic. The reason for that is less number of moles reacted. Okay, we move on to the next question. So actually, the next question, you can just move through the questions without understanding what's happening. Okay? Okay. But of course, I will just explain to you. We are looking at the acid dissociation constant. So if I am writing down the equilibrium for butanoic acid, it will be butanoic acid dissociates into butanoate ion and H+. Okay? And the Ka would be concentration of products over the concentration of the reactants. Okay, so what they're doing here is that they are setting up a buffer system. Okay, so buffer system, you need high concentration of acid and high concentration of the anion. The acid comes from the acid because it's a weak acid, not much dissociation is happening. And the anion comes from the salt. What's the salt? Sodium ethanoate. Okay. from sodium ethanoate. Okay, moving on. They are going to prepare 2 moles per dm cube of acid, 2 moles per dm cube of salt. Pure butanoic acid must be kept away from naked flames. If something cannot be put near the fire or an open flame, what does it mean? It's flammable. So butanoic acid is flammable. The next question is just your basic mole calculation. You know the concentration, you know the mass, you can find the MR. So first, you find the number of moles, okay? Mass over MR to give you number of moles. And then you want to find the volume using C and V, okay? However, be careful, your concentration is in dm cube. So your final answer will be in dm cube and you need to convert it to dm cube. How do you convert it to cm cube? Times by 1,000. So 0.25 times 1,000 should be 250. Okay, that's a simple calculation. So I hope I expect you to be able to do that. Next, a student is given 55 grams of sodium ethanoate in a beaker, so you don't have to worry about measuring the solid out. Describe the next steps the students should take to make a solution of the volume calculated in B part 1. So you've already calculated you want to make a solution up to 250 centimeter cube. Give the name and capacity of any key apparatus which should be used. Capacity means the size. For example, I want to use a beaker. Which beaker do I use? Do I use the 10 centimeter cube beaker, 100 centimeter cube beaker, 25 centimeter cube beaker? You have to list that down. This is a question where it requires you to have a photographic memory, okay? Because you should be able to imagine what is the size of the beakers that I have come across inside the lab. Okay, so of course you can't make up a beaker. Oh, I'm going to use a 65 centimeter cube beaker. There's no such thing as 65 centimeter cube beaker. Okay, there's 10, 25, 50, there's 100, 250, I believe, 500, 1 liter. Okay, so you just use the ones that you are familiar with. Okay, first, to make the solution, I need to dissolve the solid. Okay, right, dissolve solid. Okay, so what do I dissolve? Tell me, how do I dissolve the solid? With what? Put it where? So you have to describe. So how do I dissolve a solid? Sorry? Beaker, distilled water. Okay, yes. I dissolve the solid in a beaker using a distilled water. Yes, okay. Dissolve solid in a beaker, but which size beaker? Solidnya 55 grams. So I would use a 100 in a 100 centimeter cube beaker with distilled water. Okay, so I dissolve using a stirring rod, but the key apparatus here is the beaker, 100 centimeter cube beaker. That is what they mean by capacity. Okay, now then I want to transfer. When making a solution, what apparatus do I usually use? I need to transfer this contents in the beaker to somewhere. What is that? What's that? The apparatus is over there. What do we call that? Volumetric flask. So transfer the contents into, what size is that volumetric flask? 250 centimeter cube volumetric flask. And what do I do to make sure that I've transferred everything? So I don't leave anything. Yes, I wash and wash or rinse the beaker. Okay? What I mean by washing is not to throw it out to the sink. I wash it out and then I transfer into the volumetric flask. Okay, then I transfer the beaker. Um, what do I do next to top up the water? Okay, so add in the volumetric flask, add distilled water. When do I stop? At the line, at the 250 centimeter cube line or mark. After that, what do I do to make sure that my solution is yes? And mix or shake well. Okay, so those are the steps. All right, next question. The table. Complete the table to show the volumes and the number of moles. Okay. Again, I didn't know what's happening here, but I can look at the first and the second column. Okay. I know the number of moles. I want to find the volume. I also know the concentration. So I know N, I know C, I can find V. Okay, that's how I found the V here. So same thing for ethanoate ion. I know the number of moles. I know the concentration, which is 2 moles per dm cube. Then I can find the volume. Okay, so volume of sodium ethanoate ion is using V equals to N over C. Volume of distilled water, I have to make sure that the total volume of the acid, ethanoate ion, and distilled water to be 50 centimeter cube. So whatever my volume is here, I take 50 minus 25 minus 2.5. The rest will be water. Okay, so you do the same for the rest of the table. Decimal place, you follow the table. Here the decimal place is to 1 decimal place. So your volume should all be to 1 decimal place. Okay. So once you're done with that, you should have another table again. Again, I still don't know what's happening, but I just read the question. They say to give my values of minus log acid over base. So minus log of acid over base is basically minus log of this number. Minus log of 10, minus log of 6.25, minus log of 5, minus log of 2, and etc. Okay? And then this will be the independent variable, your x-axis, and y would be your dependent variable, which is your pH. Plot a graph of pH y against x. Use cross. Circle the point on the graph you consider to be most anomalous. Okay. So this is what I got. I cannot include the origin as a point because it's not 0, 0. Did you manage to draw this graph? Yeah? And did you find, well, I wouldn't consider that as anomaly because it's not too far off from the straight line. But, you know, the question says to circle any anomaly, and that would be an anomaly. What does it mean by this anomaly is that if you look at that point, it is at somewhere around negative 0.3, right? The pH of negative 0.3 should be down here. That means the pH was overestimated. The pH was higher than it should be. Okay? What's the reason or what can cause this high in pH is probably because the concentration of hydroxide ion was actually a little bit lower. Okay, they overestimated the concentration of the hydroxide ions or the number of moles of the hydroxide ions. Okay, why do I talk about hydroxide ions? Because pH is high. So pH is high indicates that it's around the it has more hydroxide ions, increasing hydroxide ions as the pH gets higher. So sebenarnya the pH is actually moles of the base is higher. So actually the pH is actually a bit lower. Sorry. The amount of hydroxide ions is actually a little bit lower, okay, than expected. So the reason for that, one reason is the moles of base is higher than what was recorded. Okay. When the concentration of acid is equal to the concentration of base. So negative log acid and base. If the concentration of your acid and base is the same, it becomes 1. Do you agree? Yeah? Number on top, number at the bottom is the same, so it becomes negative log 1. What's negative log 1? 0. So you go to 0. You read your pH at 0, which is somewhere there. So that pH is equals to your pKa. Okay? Kenapa tu? What happened? So what sort of number are you getting? 4.882? 4.82, I got 4.84, a little bit higher, but it should be okay. Yeah, did you get that value? Danesh, what's your value? 4.84. Okay. Right, so the answer is pKa is equals to the pH 4.84 or 4.82 in your case. Mine would be 4.84. Okay. Next question. Okay. Use your answer to see part 4. Okay. Use your answer to see part 4 to calculate the value of Ka. Okay. So how do we find Ka? We need to rearrange this. Okay. Ka is equals to, so the log is to the base 10. So how do we rearrange this? Log base 10. So just imagine this is y minus log 10x. So x is equals to, maths. X is equals to 10 to the power Why? What about the negative? Ten to the power of minus y. Okay, so if I were to change that in chemistry, Ka is equals to 10 to the power of minus pKa. Okay, so you just have to type in your number, 4.84 in my case. So it should be 4.84. Minus 1.45 times 10 to the power of 5. Get that? Yours is probably something different. 1.5 times 10 to the power of minus 5? Yeah? Is it within that range, or is it something odd? Units, how do we find the units? You have to go back to this expression. Ka is equals to so top mole per dm cube, mole per dm cube over mole per dm cube. So what's the unit here? Just mole per dm cube. Okay, that's how you find the units of Ka. Don't forget. So the units is mole per dm cube. Okay. Right. I'm going to take some of what I wrote down here, because I don't want to copy paste this thing. Copy. Okay, I'm going to need that. And then the Ka is proportional to the reactants. Okay. Products over reactants. Concentration of products over reactants. Okay, so the question is saying the value of the pKa is lower when the experiment is repeated at higher temperatures. So T increases, pKa decreases. Okay, what's the relationship between pKa? pKa is minus log. So that means pKa is inversely proportional to 1 over Ka. Sorry. It's inversely proportional to Ka, okay, or directly proportional to 1 over Ka, okay? So that means if T increases, pKa decreases, your Ka would increase. Do you agree? Okay, now going back to your AS syllabus, if temperature increase, which reaction does it favor? Exo or endo? It doesn't always favor the forward. Exo or endo? Temperature increase, so the reaction will take in the additional heat. Okay, so endothermic. Okay, so your Ka is big. So do you have more products or more reactants if your Ka increases? More products. Okay, so more products means you are favoring the forward reaction. You produce more products. So the forward reaction must be endothermic. Okay, this is working in reverse. Say if we're not working in reverse, say we're working forward. Okay, delta H of this reaction is positive because we said it's endothermic, right? Okay, as we increase the temperature, it favors endothermic reaction, right? It favors the forward reaction. The forward reaction means we are producing more products. So products is the top number. This becomes bigger. Your Ka increases as well. If your Ka increases, your pKa decreases because it's inversely proportional. All right. So that follows the statement. At higher temperature, your pKa decreases. Okay, so how do we answer this question? Explain your answer. Well, first we're going to say that it is endothermic. The reason for this is because Ka increases as temperature increase. All right. So that is all for this paper. And we are done for today.